So block day today, we're going to continue and do another lab, but this one's going to be a little more technical, so I want to set it up for you and show you what to do within the lab. That hopefully will get us to the math equation of Snell's law. And Friday, we will practice with Snell's law, the math part. So those will be more word problems. Some of you like those word problems because there's an answer to them that you can check. So Friday will be that. I'm going to push back. Monday we'll do review, and then Tuesday we'll set up a test. So this gives you, I'm pushing it back a day because we're learning. I feel like we can take our time a little bit more with this. So yeah. But today is block day, so this lab will take a little longer, right? A normal class period's 45, block day is about 90. If you're taking 90 minutes, that's okay, because it's a block day video. If you're taking more than 90 minutes, maybe ask me some questions. If you're taking like 10 minutes to 20 minutes, you might be missing something. Yeah. So we've been looking at refraction, and you'll have noticed that light bends when going through different mediums. So I have a couple pictures here. If you've ever seen in your glass of water and you put your spoon in or put a straw in and notice how the light changes, and it looks like it's coming from a different direction even sometimes. Or if you ever go to Brookfield Zoo or some other zoo and you can see through the clear glass with the water, like the above and below don't always match up. What's going on? Well, the light is getting refracted, and our eyes are trying to perceive the light as coming from straight forward, even though technically it's bent as it comes through the lens. So we call this idea refraction, and hopefully you've downloaded the notes. But refraction is the change in direction of a wave, in this case a light wave, as it crosses the boundary between two mediums. And this happens because light is actually going to be changing speed as it goes through. So if it's going from a less dense substance to a more dense substance, so maybe from like air to water, air to oil to glass, air is pretty light. The light comes in, and if we draw our normal line, if it's going from less dense to more dense, it's going to bend inward. All right, it slows down and bends inward towards the normal point. If these were the same material, the light would just keep going straight forward. But because it's slowing down as it gets into a more dense substance, it's going to bend towards the normal. Similarly, if we go from a more dense, so say we're going from water more dense to less dense, then it's going to speed up, and it's going to speed up away from the normal, and so bend closer to the surface of the medium as it goes through. So these two situations can happen, and both of you just gotta remember, if it's less dense to more dense, it's bending in. If it's more dense to less dense, it's bending out as it's speeding up. The amount of bending of the light is given a number, and we call this the index of refraction. And we represent that with the letter N. And n is pretty easy to find. We know the speed of light is c. c equals 3 times 10 to the 8th meters per second. N is just a ratio. So it's the ratio of the speed of light over the speed in the medium. So the speed of light in a vacuum over the speed of light in the medium. Speed of light in medium. And each material has its own index of refraction. And this will become important because we noticed a relationship to these angles. So we already know the angle of incidence, right? We know the angle of reflection. Angle of reflection is there. This guy is going to be the angle of refraction. So we're going to call it angle 2, angle 1 and angle 2. And if we know the index of refraction for both of these substances, we can figure out what angle it's going to bend in. There's a relationship between the two. A lot of people discovered this law before, but the one we give credit to and the one whose name gets it assigned is this guy called Willebrord Snellius, who's one of my... I just think he has the most Harry Potter name in physics. Don't know much about him, but love his name. He came up with what we now call Snell's law. And Snell's law, to give you a picture, if we have a light ray coming in, right, we call it, it has some angle, theta 1. It's going to bend in because N2 and N1 are our substances' index of refraction, right? And this is our angle of refraction between the normal and the light ray. So it's kind of opposite. The equation looks like this. N1 sine of angle 1 is equal to N2 times sine of angle 2. And I think you guys have learned sine, cosine, and tangent in geometry, whether a few weeks ago or last year, depending on what class you're in. We get to use sine in physics, and it's kind of cool that it shows up in the real world, that light knows how to bend in relation to the angles that come from it. So I just think it's interesting when you have math things that don't seem like they apply anywhere. They apply here. This is like real world application of stuff. So this is our equation. Looks a little scary. You can use your calculator. I think you got to use your calculator, right? If this is 39 degrees, we plug in 39. Sine of 39 degrees is whatever your calculator spits out. Might want to have that next to you. So this will set us up for the lab, right? We use Snell's law in the lab. I want you to go to the phet simulation, and for part 1, you're going to choose prisms, and you're going to set up the laser boxes and figure out how does light actually reflect through these different shapes. So if we're on the phet simulation, you have these shapes down here. You can put on multiple beams or one beam. Take a shape. All right, what happens? Doesn't look like much is happening. Okay, cool. So I'm going to draw my laser beam going straight through because that's what it looked like happened. All right. Now we want to angle it a little bit, so let's angle it. Oh, interesting. The light ray is refracting just a little bit, but notice that it comes back parallel. afterwards. So I could show this as light ray bends in a little bit and then comes back out. All right, what happens there? Change shapes. You have a triangle. This is a right triangle. I think they have an equilateral in here. Use the equilateral. That's fine. So just copy what you see the light rays doing. You can do multiple beams as you see fit. You can even change the color of the beams. You can change the environment that it's in. So you can put multiple ones together. So step 3, use the glass semicircle. And then step 4, try to put multiple shapes together. Like, what sort of pattern can you make? Kind of like send the laser in all different directions. For part 2, this is where the index of refraction and Snell's law come into play. Right? So the index of refraction, don't forget, is the speed of light. Let's change. In vacuum over speed of light in medium. So C over V. Light travels fastest in a vacuum, and so that if we're in a vacuum, then, you know, C divided by C, the medium is the vacuum, C divided by C is just going to equal 1. So the index of refraction for air is 1. Or for a vacuum is 1. For air, it's slightly more than 1, like 0.0003. We're just going to say, yeah, that rounds to 1. So N of air is equal to 1. In this lab, I want you to find N of glass. All right, what's the index of refraction for glass? And a mystery substance. So you can choose water, you can choose mystery A or mystery B, if you would like. The angle to which the light will bend upon passing, this is Snell's law. And the symbols 1 and 2 stand for the angle of incidence and the angle of refraction. All right, so first substance, first angle, second substance, second angle. The way we can measure this in your lab is you're going to use that semicircular piece. So we can get rid of this guy, put on this, get our semicircular piece. You're going to want to flip it around. And hardest part is going to be you want the laser to hit the middle. All right, we can turn on our protractor, and we have to line up our protractor with this guy. So if I angle this, try and hit it middle, and you can tell it's in the middle when this line is pretty straight, so it doesn't change as it comes out. If I move it over here, notice it's like changing. Oh, that's not helpful. But as you bring it closer, you can get it to line up. And then we want to keep that angle. So let's bring our protractor in, set up the protractor about here. And from here, we can measure the angle of incidence and the angle of refraction. So notice between here, here's my normal. You can even turn on a normal line, right? Normal is going to be between here and here. That looks like 10, 20. It looks about 20 degrees. All right, so my angle of incidence is 20 degrees. All right, so if we do our normal, this is our theta 1. And then theta 2, still have your normal. All right, we want to measure this right here is theta 2. So always remember you're going from the normal, not the straight line, but the normal line. So if I go back here and I look, it's about 10, 15. So it looks about 15 degrees. And that would be theta 2. All right. In my chart, all right, I mean, we have 20, so we could fill in. Angle of refraction would be 15 degrees, right? Sine of theta 1, go to your calculator. Make sure it's in degree mode. So if some of you need to change that, you go to mode. It's next to the blue second button. Put it into degree mode. And then sine of 20 should be 0.342. And sine of 15 should be 0.259. You can round. Don't worry about this column. We're turning off the reflection. If you're curious about this, you can turn on reflections, but that might be a little confusing with what's going on. So there are some reflections, but don't worry about it. We don't need that there. So you're filling in, try and have the angles of incidence change, so 0, 10, 20, 30, that way. Measure your angle of refraction. Find sine of theta for each of them. Down here is where you're going to graph. So n1 sine theta 1. I already know sine theta 1 and sine theta 2. We're going to, the fancy term is called linearize the data. But if you think of sine theta 1 as your y, and sine theta 2 is your x, well then we could find the slope, because we know our columns y and x. So this is going to be your y column, and this is going to be your x column. So when you go into Desmos, you can put in x and y on your data table, all right? Or use whatever you can. So your x-axis should be sine theta 2, y-axis should be sine theta 1. So you can plug in all of these decimal points into that data table. It'll be like x1, y1. Plug all those in, and then remember to fit a best line, you need y. It'll probably be y1 is that little tilde proportional to mx1. And whatever m comes out, that's going to be n2, and that will be your index of refraction for class. Give it a shot. Once you have done that, you get to choose the next one. So there's 3 different substances, and I just want you to run through it again so you can choose water, mystery A, or mystery B, right? And, you know, use your different lines. So you have to change the angle. All right. Oh, look, 0, 0. If I do mystery A, like, what's the index of refraction? That way. Give it a shot. Play around with it. You're changing the angle. So as I change this angle, I need to change my protractor. So now this would be, let's see, 40 degrees. 40 degrees would be like that. So I need to measure that at 40. And voila, you could find your index of refraction. That looks to be about like 13. I would say 13. All right. So yeah, keep going. Try your best. See what you come up with. If you have any questions, please feel free to send me an on-campus message. I can do my best to help. Maybe go back, watch it again to get an idea. But once you get into the rhythm of it, you should be fine. And let me know what you find. Sound good? Go team!